of authority in the church or princes and so on who were against him. Again, things are complicated. It's not very simple. But there's this famous saying that first what we know is the sentence, karar, of the church court, the Inquisition, was that Galileo was going to promise not to discuss, not to teach, not to write, etc., his ideas about the solar system and the motion of the earth. And of course he was under a lot of pressure. There was a physical pressure. There was a danger of being put under physical torture. I mean, they didn't do it, but there was a threat because they did it to other people. Okay? So he recanted. He said, he signed this document saying, I'm not going to say these things, teach these things. And then he was put under house arrest. He couldn't leave his home for the rest of his life. But he did have contacts. He wrote and he published, etc. But anyway, the legend, it seems, is that Galileo said, or maybe sort of under his voice, murmured that these famous words, "Eppur si muove." Ne yapayım dönüyor. Whatever I say or you say, the physical world has its own dynamics. It does whatever it does according to laws of nature, not according to what is considered to be correct to say. Right? He probably didn't say it, because to say it, at least to say it loud, would be a very stupid thing. While you are signing it, I signed it, but he wasn't a stupid man. He probably didn't say it. But I looked it up in the Wikipedia, and apparently the first appearance of this legend was some 50 years or so after Galileo's lifetime. But it is nevertheless a very good way of expressing something basic about science. It's exactly like that. And it's not just about rotation of the earth or the fact that the earth moves around the sun. Whatever it is that you learn about the way the world works is true because that's the way the world works. It's not true because the dominant political or religious or scientific authority or the best textbook says so. Nature doesn't care what you say. It doesn't care whether you believe this or that or whether you do your experiment right. Okay? And that's what this word, although Galileo probably didn't say it, it's a very, very brief summary of what science is about. We try to, the word is there for us to learn and to enjoy. Okay? And if we are clever, we learn about it systematically. We try to use our knowledge of what we learn with some judgment. Okay? But it's there and it does its thing no matter what we do. No matter what's fashionable. No matter what's allowed. Okay? So these three words, which Galileo probably didn't say it, but could have said it, it represents his whole life of work, and it also represents what science is about. The whole philosophical point of science is. It is there, and it does its things. And there's nothing I can do about it, except learn. Okay? Now, a very important thing about scientific statements is that they are conditional. Conditional in Turkish is şartlı. What happens depends on the conditions, particular conditions there. in principle. For example, if I drop my keys, they fall. This doesn't face much condition. Anything near the surface of the Earth always falls towards the Earth. So the conditions here are pretty loose. But if I looked at objects falling not on the surface of the Earth but on the surface of the Moon, they would fall not towards the Earth but towards the Moon. So that's a different condition. If you now refine, go into more detail about your experiment. For example, you say that something near the surface of the Earth will fall. And it will fall down with increasing speed, faster and faster. And the increase of speed, which we call acceleration, is, I have measured it, it's 9.81 meters per second square. Don't worry if you don't understand the units, we'll learn all of this later, but it's something that I measure. And the numerical value in my units is 9.81. True? True. Where? Here, let's say, when I do the experiment. But then we have to realize that if I do the same experiment on top of a mountain and compare the results with sea level, if I do the experiment at different latitudes and on Earth, the result will be a little bit different. So if I say I measure 9.81, I have to say I'm at this altitude, at this latitude, here I measure this. This is conditional. Okay. So depending on the experiment, there are always things that depend on conditions. The more detailed, the more conditions. The more general, of course, if you go towards in the direction of generality, it becomes everything near the Earth falls towards the Earth. This is true. Every two things attract each other by gravity. So if it's near the Moon, it will fall towards the Moon. But the Moon is attracted by Earth, etc. That's a more general theory of gravitation. Okay? The validity of that is much, much more general. But there is still a limit. Because if you are studying the motion of objects, you can say, does the way objects move depend on their speed, how fast? Now, people before Galileo, and Galileo himself, and Newton, and all these others, all the classical physicists thought, no. We have certain laws of motion that we learn from experiment, and whether an object is moving this fast, or faster, or slower, or this way or that way, the same laws seem to hold. When two things attract each other by gravity, the sun and a planet, let's say, they move in orbits around each other, and it's always like that. It was only in the 19th century that it was realized there was a condition. Objects that move very fast. Very fast, what does very fast mean? In science, you don't say just very fast, little fast, you know. It's not that loose. You have to say, compared to what fast? Things that move at speeds that are close to the speed of light have somewhat different laws. So the law of motion that you write down about speed, about velocity, about acceleration, depends on depends on what the speed is that you are talking about and how fast it's moving with respect to you. In the 19th century, it was realized from electricity and magnetism and light, it was possible to measure already before the 19th century the speed of light. It seemed that the speed of light is constant. Well, okay. But then, if I measure the speed of light here, and if I put the same experiment on a train platform and measure it while the train is moving, classically you would think that if somebody moves in a train with velocity 3 meters per second inside the train car, and the train is moving with, I don't know, 10 kilometers per hour, and I measure this guy's speed from this platform, his total speed is 10 kilometers per hour plus 3 meters per second. You just add it. If this is true for light, then I measure light from the train platform, and the train is moving, and the light is moving, light is made with a flash bulb inside the train. I would measure something faster. This kind of experiment was done, and it was found that something very strange is happening. The velocity of light, no matter who measures it, I measure it from here, and somebody else measures it from an airplane, they get the same speed. This means the law for adding velocities